Oh, hey, welcome everybody. Welcome to our virtual lecture. I still see some folks coming in. Come on in, come on in. I'll get started in a few minutes with our lecture on chapter 4, and I would like to get started from section 4.5, where we stopped last week on concentration. That is the last thing we looked at last time. Before we get started with chapter 5, I want to kind of like review real quick what we went through last lecture. Allow me to share my screen here. If you have any question, please use the chat box on the Zoom conference. Right now, I'm gonna share my screen and kind of like go through section 4.5. It's pretty much straightforward subtitle. You can easily master the concept of concentration. I know you already covered this in Introduction to Chemistry, or if you are taking the course, this should be coming back to you. Concentration. It is an important chapter you need to master, you need to understand, all right, in terms of calculating the concentration, that is the relative amount of number of moles in volume of solution. Remember this equation, and I'll give you in the next exam. Molarity is given by the number of moles of solute, all right, of volume in liters of solution. That is what we looked at last time. For some reason, you can't see my white screen. Let me see what's going on here. It should be, hold on, you should see my white screen. Yes, that is what I was showing you, and I think you didn't see the equation. This is what we looked at last time. Given the mass of a solute that's being dissolved in a given amount of solvent, you should be able to find the molarity. Quite often, this top part, number of moles, you may be required to determine using the mass of the solute, all right, mass of solute, what is being dissolved, of molar, this is molar what? Molar mass. You may be required to use the periodic table. Use periodic table. If you are not given the molar mass, use the periodic table. Once you get the number of moles, you plug it in the equation. And then, of course, you can rearrange this equation to find the volume in liters, to find the volume in milliliters, given the molarity and the number of moles or grams. This is one equation used to determine the molarity of a solution. Now, there is an equation we call dilution law. You'll see this in the lab, dilution law, or sometimes we call this dilution equation. And you are expected in Chem 2 to remember this equation, M1 V1 equals to M2 V2. This could also be M, all right? This could also be M, this could also be MC, VC for molarity, that is concentrated, molarity of the concentrated solution times volume of the concentrated solution equals to molarity of the dilute solution times the volume in volume of the dilute solution. We have four identities in this equation that you should be able to rearrange. You should be able to rearrange. Now, I know I solved this. problem on the PowerPoint slide here last time, but from equation, looking at equation 1 on this slide and equation 2 on this slide, you should be able to recognize and identify which appropriate equation you're going to use given the formula sheet. You will have to write down the notation. You assign the volume and the molarity, the concentration to the numbers given. For example, here, how many milliliters of stock solution? This is the unit for volume. So you're looking for V1, which is question mark. M1 is 6.0 molar nitric acid. You have to use to prepare 110. That means V2 equals to 110 ml, and M2 equals to 0.500 molar. From this, from dilution law, V1 equals to M2 V2 of M1. You just plug in the numbers and you end up with the correct number. Pay attention to significant figures. Sometimes in the online homework, you may have more than what is required in the multiple choice, and probably when you select, you will be wondering what happened. I'm using my calculator. I know I'm using the right equation, and sometimes they expect you to still remember the laws or rules for significant figures, multiplication and division. If I see these are two significant figures, and most likely you'll express in two significant figures. Now, here is the summary or the flow chart of stoichiometry to this point. This slide summarizes, all right? It summarizes the equation used to find the identities you're looking for, all right? Changing from the mass of the solute to moles of solute, you use the molar mass. If it is an element, look at the periodic table. If it is a compound, you have to determine the molar mass or formula weight of that substance or compound, and then you quantify that. To relate now compound A and B, use the coefficient in the balanced equation, And if you have the moles, want to find the molarity of the solution, you use the volume of solution of B with the number of moles, and likewise for B volume, using the molarity equation. It might look like an abstract, but it just summarizes some of the equation we looked at before. And if you look at this is math, and like I said before, you cannot read math. You have to practice, okay? You have to practice, and with practice, you should be able to master the concept of molarity. Any question on molarity and dilution law? If not, there is something I want us to look at. Is important in chemistry. That is the solution stoichiometry. Remember how we define stoichiometry. It's the quantitative relationship of reagents and product using the coefficient in the balanced equation. In particular, we look at the relationship in titration. Titration is basically determining the concentration of a known solution using what we call standard. In titration, an equipment we call purette, you may have used this before. This is called purette. You may have a known concentration or molarity. What goes in the purette here is called the standard, all right? Standard means known molarity or concentration that goes in the puree. We call that puree. And in titration, you'll have known volume. That means a known concentration and known what? Known volume of your analyte. We call this analyte. What you are analyzing is called the analyte. You want to know the concentration. You will titrate fast as what we call the standard. The standard is, we know the concentration, all right, the molarity. And for titration to be successful, there is what we call the indicator, all right? We will have an indicator in there, indicator, all right? It indicates, from the word indicator, it indicates when titration is complete. How do you know that the titration is complete? When you see a color change here, when you see a color change in your titration, and then you know it's time to stop. It's time to stop. It indicates the equivalent point. Indicator, this indicate equivalent what? Point. And what is equivalent point? Equivalent point in titration is a point in titration where you have equal amount of moles of the titrant or the analyte and the standard. In other words, initially I have the number of moles of my analyte, but I don't know how many moles. I will continue adding the standard, all right? Adding the standard, remember the indicator is added in there to indicate the equivalent point. That means at that point, the titration will be complete. In other words, if you look at this, let me give you a scenario here that if we have 5 moles, if I have 5 moles here, if I have 5 moles in my analyte, I'm just making up that number, I will need 5 moles of the titrant here. I will need 5 moles if the mole ratio is 1:1 for complete neutralization. So I'll need to dispense 5 moles into the analyte, into what we are analyzing. And if I add 6, if I add an extra, based on the stoichiometry in the balanced equation, if I add an extra 1 mole to make it 6, that 1 mole will react with the indicator, all right? And once it reacts with the indicator, it will form a complex which has a characteristic color. For example, right here, there is pink, and you know it's time to stop. Now you'll have to read the volume, that how many ml did you dispense into your unknown solution for complete neutralization. You have to picture that. You got to understand how that works, so that you wrap around the problem. I'm going to show you problem, but that is the titration. You will have to start from the top here. It could be 0.00 to somewhere where the volume, this will be your final volume. Final volume is the volume you will stop once you see what? The color change. And then you calculate what is the volume. So if I knew the concentration, if I knew the concentration of the standard and the volume required to neutralize the unknown, you use the stoichiometry to determine the concentration of your unknown or your analyte in this case. So let's see how are the problems presented in titration. It is similar to the concentration problem, except here we are dealing with the solution. So volume of the standard solution, somebody who doesn't relate to this whiteboard diagram will say, what is the standard? Standard is what always goes in the puree. Next time, ask your lab instructor that, is it true always that the standard goes in the, unless there is a specific lab Generally, rule of thumb is the standard goes in the puree. Use the molarity of the standard. Remember, I said the known molarity of the standard. So whatever goes in there, we know the what? We know the concentration or molarity is the same thing. And then we use, all right, we use the mole ratio coefficient in the balanced equation to determine the number of moles in the unknown. So if I know using the volume to reach the equivalent point, if I know the volume used to reach the equivalent point by the color change, I can use the molarity, which is the concentration, and the volume. You see this? Number of moles is given by volume in liters times the molarity of the standard. All right, the standard. This will tell you the number of moles, all right, number of moles of the standard use, and then use now the coefficient in the balanced equation to determine the number of moles of your unknown. For example, here, you can see that I pick 5, that if mole ratio is 1:1 or the coefficient is 1:1, I'll need 5 and 5 to neutralize that. And then if I started with 5, remember the volume of the analyte, what you are analyzing is known. You'll always be given. You use the moles from the mole ratio, all right, and the volume of your analyte to find the molarity or concentration. Please don't, make your life complicated thinking that molarity and concentration are different terms. Sometimes the word concentration, find the concentration, can be interchangeably used with the word find the molarity. It's the same thing. That's why you see here. So the objective in solution, all right, the objective in solution stoichiometry is to move from point A here to point B here. And this is the roadmap, all right? This is the roadmap. It might sound like a long route, but it is not once you know. I'll show you, an easy way of figuring out without having this diagram. You may have this diagram in an exam, or you can reproduce in an exam, but how will you apply to the problem? How do you relate to the problem? Okay. Now, as we go through, I hope you are aware that the bold terms, sometimes in the lecture PowerPoint slide, in the text, you should know what it means. I've defined the word standard. Solution with known concentration is called the standard, and it always goes to this classware. Long tube we call the puree. I don't know, let me just grab one here. If you can see, use the chat feature and say you can see the puree. I do have the puree. I don't know if the background will let you see. Can you see the puree? Somebody use the chat feature and say yes, no. This is the puree, and then this is the we call this the stopcock, and perpendicular close, and the volume start from 0 to 50 or 25, whatever you have. I don't know if you can hear me. No one is responding. Can you see? Can you see? You can see. I know you see this. So this is the same one we have here. We call this the stopcock. When it is perpendicular with the parallel, it is closed. This is open, like it will drain now the standard to our analyte until the color changes, okay? So this is what we use in titration. We use that in titration. And always the standard goes in the puree. We call that standard solution. Equivalent point I had mentioned earlier on, you have to know, and this is going to come down in Chem 2. Equivalent point is a point during the titration where you will have dispensed equal amount, or you will have neutralized, whatever if it is acid-base neutralized, you will have neutralized completely the number of moles, or you'll have consumed the number of moles of the analyte. We call that equivalent. If you want to program your brain from the word equal, All right, that means equal number of moles, and it is indicated by color change of the indicator. So next time you see the procedure saying that add 2 to 3 drops of indicator is so that it signifies the end or equivalent. That means end point to end, that you should stop titration and stop, cut it off. All right. Don't add any more of your standard into it is indicated by the indicator. It's good to know what those statistics are wrap up of what you will see. You will come across the equivalent point or the concept of titration in the lab. Here is the problem now, all right? Here is the problem on titration. What volume of 0.115 molar hypochlorite solution is added or needed to neutralize 0.0875 NaOH. This is 1-to-1. The thing is, they expect you to be able to write the balanced equation, all right, for your neutralization reaction. Here it is 1-to-1, 1-to-1. In other words, this is the equation. HClO4 aqueous reacting with NaOH, all right? This will always form a salt, all right? ClO4 plus H2O plus H2O. This is liquid. This is acid-base neutralization, so it always produces liquid H2O and a salt ionic compound. We care less about the product so long as the equation is balanced. By inspection, the equation should be balanced. It is 1 to 1 to 1 to 1. We care less about the product. Now, in neutralization, this means for every 1 mole of the acid, 1 mole of the base is consumed. 1 mole of the acid react with 1 mole. This is just, you know, the mole ratio. We indicate this as 1 to 1 to 1 to 1. We call the coefficient in the balanced equation mole ratio. Mole ratio. Now, what I have, I found it effective in my view in titration is calculating the concentration and finding the number of moles of the acid and the base respectively. Keep the information for each reagent. My broken line is to find the information for each one of them. What we know as far as the acid is volume, and you have to use volume in liters. What volume? That is what we are looking for. Molarity for this is 0.115 molar. For the base, we have 0.0875 mole. All right. What volume? We are looking for that. This is the molarity of the base. Is needed to neutralize. So we know what? We know the volume of NaOH, and the mole ratio is 1 to 1 to 1. So if we know the number of moles, all right, if we know the number of moles of volume and the molarity required, we are looking for moles of NaOH. So our number of moles is given by what? Volume or molarity times what? Volume in no, it's volume in liters over what? Volume in liters over molarity. Volume in liters over molarity for the acid. So if we know the number of moles neutralized 0.0. Number of moles, mole ratio is 1 to 1 to 1. So if we know the number of moles, here there is, we need to know the volume of NaOH. We need to know the volume right here. Something is missing here. Let me see. Hold on, let me check. Something is missing in that problem. Volume. I need to find the number of the volume. Should have been given the volume of NaOH. I need to find the volume of NaOH. We should have the volume of NaOH. Yes, there is something missing here. This is problem. For those with the text, this problem is page 158, number 4.81. What is missing in that problem is here we have 50.00 ml. So I missed the volume. I missed the volume in the problem here, okay? So some information was missing in my learning check. We need to know the volume. So this is the volume of NaOH. This is the molarity of NaOH. We want to know the volume of the acid required to neutralize this. So from the molarity, we need to find the number of moles. What will be the number of moles for this? What will be the number of moles? If I know the number of, if I know the volume and the molarity, I will use this equation. Number of moles is given by what? Is given by molarity times volume in liters, which is 0.0875 moles per liter is the same as molarity times volume in liters. 50 is 0.050 liters. I change that to liters, change this to liters, and we will get the number of moles. Why am I doing this? So that I use the mole ratio. This is the number of moles is 0.0875 times 0.050, okay? And here is the number of moles, 0.004375 moles of NaOH. I use the information given for NaOH to find the number of moles. So here is 0.0048. I know the number of moles. Maybe I need to write this so that you see clearly the number of moles is given by 0.004375. Let me pause here. Remember I said that 50 ml is missing here. Look at problem number 4.81 on page 158. So the information for, I have to use the molarity equation to find all the information I need for each reagent. I'm using this broken line to separate. Now, from the mole ratio, it is 1:1. So I can say that for every moles of the paste neutralized, the same number of moles of the acid are consumed. So here, number of moles will be the same. Here is 0.00437 mole ratio is 1:1. If it is 2:1, and then we will multiply pi 2 on this side. If here is 2 and here is 1, and then we will divide pi 2. You use the mole ratio. Somebody say they cannot see. Let me see. Kenneth, can you see now? We're all on the same page. Ken, can you just respond? Can you see? Ken? All right, thank you. All right, yes, somebody explained. Jennifer, you wanted to know the number of moles. Let me pack up. There was a typo on my PowerPoint slide. As I say, you'll be given the information for, enough for you to proceed with calculation. So at the outset, I needed to neutralize 50, all right, 50.0 ml. That's why I'm writing 50 ml per load sodium hydroxide. And the concentration of sodium hydroxide is 6 molarity. So I know mole ratio here is 1:1. So I need to know the number of moles of NaOH neutralized. Using the molarity equation, this is how I found the number of moles of NaOH using the volume in liters and the concentration, which is molarity. Don't use 50 ml. No, the definition of molarity is volume in liters. That's why I'm using the subscript. With that, I know the number of moles of NaOH. All right, number of moles of NaOH is right here. From the balanced equation, the mole ratio is 1:1. This 1:1. So since mole ratio in the balanced equation is 1:1, all right, it turns out that it will be the same number of moles of HCl required to neutralize since it's 1:1. Now, Jennifer, if here was 2, if our coefficient here was 2, that means we will multiply pi 2 the value we have here. If here was 2 and here is 1, and then we will divide the value, this pi 2, to get the number, because it is 1:2. 1:2. The reason why I like this, so that I will answer the question based on what we know with the molarity. Before I calculate the molarity, are we to say, am I clear, Jennifer? Are we together? Thank you. Yes. So look at the broken line. Look at my broken line right here. This will now give me information. I need to find the volume of this. If I know the number of moles and I know the molarity, I can use, and remember I have to write the subscript L, it will be volume in liters. Sometimes they might ask you, what is the volume? And the multiple choice is in ml, 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 ml. You have to use liters in calculation, and then you change to ml. In this case, we know the molarity. Therefore, all right, therefore, number of moles of HClO4 is the same, equals 0.00437. It's the same because mole ratio is 1:1. Using the molarity, from the molarity, volume in liters, rearranging the equation is given by the number of moles of HClO4 over molarity of HClO4. We know the molarity, all right? We were given the molarity. We used the stoichiometry 375 over 0.115. This will be moles And sometimes this is given as moles per liter. Moles and moles will go away, and you'll remain with volume in liters. Volume in liters. So 0.004375 divided by 0.115, and this is 0.03804. It's more than what we need for significant figures. This is in liters. Then you multiply per 1,000, it will be 38. All right, 38.04 ml, just for significant figures. For significant figures, this is how to find the the volume using the titration. Somebody was asking, can we use M1 V1? There is a typo here. Please allow me to, all right, here. It's not going to work. Let me just go back here, because there is needed to neutralize 50.00 ml of this one is page, this problem page 158, number 4.81. Okay, so that one doesn't create some confusion. I had to check because I had missed that in the calculation. So all right, David, you are asking why can we use M1 V1? All right, M1 V1. That is a good question. It will work. All right, it will work if it is 1-to-1. And remember what Jennifer asked, and I gave out an example of when the mole ratio is 1-to-1. David, if mole ratio is 1-to-1, it will work. But in the event that the mole ratio is not 1-to-1, and then you have to, you have to use the stoichiometry to do that. For most part, it works. But sometimes it will not work if the mole ratio is not 1-to-1. For example, in the subsequent. We'll see that. Let's see in the second equation where it is not 1-to-1. What volume of 0.128 molar HCl is needed to neutralize 2.87 grams of magnesium hydroxide? Well, this is just pretty straightforward. Let's see. In this one now, let's see how 1-to-1 will not work, and maybe it will shed some light for you, David. If this problem, we write first of all the equation, HCl aqueous plus magnesium hydroxide, OH magnesium hydroxide equals to, or going to, magnesium chloride. That is the equation for magnesium chloride. You have to play with the rules. Plus H2O plus H2O. It form a salt and a water. This is aqueous, is soluble in water. When we dissolve that. Now, if I look at the mole ratio, we need to balance the equation. On the product side, we have 2 hydrogens. On the reactant side, we have 3 hydrogens and 1 chlorine. We need to balance the equation. That means we're gonna need that 2 here to balance the equation. There is 1 right there. There is 1 right there. And there is 1 right there. And I think, let's see. 2, and then I put a 2 in front here to balance the equation. 4 hydrogens on the product side, 4 hydrogen on the reactant side. How do you know how to balance the equation? That 2 times 1 hydrogen, 2, plus 2 times 1 hydrogen, that's 4. And 2 times 2 is 4. And then oxygen, 2 times 2 is 2, 2 times 1 is 2, magnesium is 1, and the equation is balanced. The equation is balanced. If I draw, what will happen? If I draw the broken line just the way I did and write the information for each species, what do I know for each reagent? What I know for the first one is what volume. That means I'm looking for volume in liters. Question mark. What volume of HCl? Molarity. I don't know the molarity. Oh no, we are given the molarity. I'm sorry, 0.128. Watch how I'm just gonna, fill in the column or supply the information for each reagent. Number of moles, I don't know either, right? But I can determine later on. This is question mark, that is question mark. For the second reagent, can somebody Google for us molar mass of magnesium hydroxide? Molar mass of magnesium hydroxide. What is the molar mass of magnesium hydroxide? Molar mm of Mg. This is magnesium hydroxide. What is the molar mass? You can Google out. Somebody give us the molar mass with your smartphone. What is the molar mass? I turn it off. I turn off my cell phone. Can somebody Google out magnesium hydroxide? Yes, thank you. So this information here, 58.3197, this is grams per mole. The reason why I'm asking this, I want to change the mass to moles because of the mole ratio. You relate these moles to moles. Therefore, we need to change this to moles by dividing it by molar mass. So 2.87 grams of magnesium hydroxide times the molar mass as a conversion factor, 150, not 158, but 58.3197. This is grams, and this is 1 mole. We need to know how many moles are in 2.87. So 2.87 divided by what? Divided by 58.3197, and that is 0.0492 and give more or 4 significant figures. So this is the number of moles I do have in this. So number of moles here is 0.00 what? 00 not 0, but 0.44921. This one right here, remember, in neutralization reaction, hydrogen ion react with what? Hydroxide ion to form H2 on that side. So for every 2 hydroxide here that react, 2 hydrogen ion are consumed. So even though there is 1 in front of magnesium hydroxide, the mole ratio is like 1:1. It's the same as, 1:1, because for every 1 magnesium hydroxide dissolved or neutralized or consumed on the balance equation, 2 hydroxide are produced, which will react with the 2 hydrogens. So it's safe to say what? It's safe to say that the mole ratio is 1:1, which means number of moles here is 0.0492 1. From here, we can find the number of moles. all right, number of volume, sorry, volume of, therefore, volume in liters of HCl is given by the number of moles, all right, of HCl, of molarity of HCl, which is number of moles is 0.04921 of molarity, which is 0.12828. You can express it in liters, you can express it in milliliters. So when I divide that, 0.04921 divided by 0.128, this is 38.4. No, 300. This is 0.3845 liters. You can change to ml, which is 384.5. This is the same as 384. You can change that to 384 right there. That is the liters. So be careful when you are given hydroxide. Look at the equation if it is mole to mole ratio. I know if you go to YouTube or read in the text, it might the author might use different approach, but this, you know, this practice of just drawing the parallel and see what I know, I will be using over and over the same equation of molarity. If you took note of how I solved this, I used the molarity equation, that what do I need? What do I have this volume? How do I find the number of moles? And then the only addition is paying attention to the mole ratio in the balanced equation, and everything will work out. Most problems you will see, especially even in the lab, is the mole ratio is 1:1, and common titration problem is HCl and sodium hydroxide, which mole ratio is 1:1. If it is not 1:1, you got to pay attention to that. With that, I want to just stop there, and if there is anything. No, Dorian, that is a good question. You say you thought it was 1 to 2. Yes, for a minute I thought it was that, but if you look at this, the number of hydroxide, and that's why I have hydroxide here, for every 1 mole of magnesium hydroxide consumed, let me show you this. For every 1 mole of MgOH dissolved, it will produce Mg2 positive, this is the cation, and it produce 2 OH negative ion. Likewise, for HCl, when we balance the equation, remember this was 1 in the balanced equation, this will produce 2 HCl, 2 hydrogen ion, and 2 chloride ion. We care less about the chloride and magnesium. All we want to do is neutralization. Neutralization is an hydroxide reacting with hydrogen ion or hydronium ion. So if you look here, Dorian, it is 1:1 or 2:1 is the same thing. So it's 1:1 from here. I thought it is 1 to 2, but not. There are some situations where it's not going to be 1 to 2, and I can give you an example on balanced equation, not to solve problem. For example, NaOH, or rather this, let me show you an example where it's clearly not 1 to. So we only do the ratio, yes, the ratio of OH to H plus. That is what you need to pay attention. It's safe to say that. And look at that, David. And here is an example. I don't have the actual problem here, but I'll show you an equation where it is not 1:1 or 2:1. Let's say sulfuric acid. This is sulfuric acid. It's aqueous reacting with NaOH. This is a base. So we know that OH and hydrogen will react to produce sodium sulfate plus H2O. This is acid-base neutralization. So if we balance the equation, that means we need a 2 in front of what? We need a 2 in, no, I didn't mean to. So we need a 2 in front of NaOH. So look like this is also going to be the same thing, 1 to 1, and we need a 2 in front of that. So the equation is 1 to 1 to, it's 1 to 1 or 2 to 2 again. Yeah, pay attention to that. 1 to 2, NaOH, HCl, it produces 2 hydrogens and 2 hydroxide to produce HCl to give you that. So I'll look at OH. Look at the OH. I'll try to set a quiz for chapter 4, do the assignment on mastering my lab. Any question on chapter 4, please? All right, if there's no question, let me just close this or minimize, and we will shift gears to chapter 5, which is thermochemistry. And the first 4 chapters, all right, the first 4 chapters deals with, you know, matter, something we can see, something we can touch, we can feel, all right? Remember how we define matter? All the chemical reaction we talked about has to do with matter, something we can see, something we can, and the purpose of this is to understand the world around us. Now, to fully understand the world we live in, scientists want us to also look at the, you know, to really fully understand the world around us, we need to look at the energy component of chemical reaction. We mentioned that before. And chapter 5 is, or specifically deal with those reactions which produces heat or absorb heat during chemical reaction. You will see in details in chapter 19, thermochemistry, all right? And thermodynamics. Thermochemistry is what we kind of took at in chapter 5. And by end of this chapter, we'll look at the concept of energy, first law of thermodynamics, which states that energy cannot be created or destroyed, all right? That's the first law of thermodynamics. I know you know the law of energy conservation, first law of thermodynamics. There are 3 laws. Second law and third law you'll cover in Chem 2. Now, section 5.3, enthalpy of reaction is basically heat of reaction. We'll see how to determine the heat of reaction. We're gonna talk about the exothermic reaction. I know you know what exothermic reaction is, you know what endothermic reaction is all about. And how do we, in section 5.5, we'll see how to determine the heat produced or released or absorbed during the chemical reaction. Chapter 5 deals with the technique, calorimetry, is the technique of determining the heat release or absorbed during chemical reaction. And some chemical reaction, it is not easy to determine. After looking at section 5.5, it's not always that easy to determine the heat of reaction for a chemical process. Some reactions are so complex, and there is a way of determining the heat of reaction using the Hess's law, that's section 5.6. And lastly, the food we eat. Sometimes you are curious or you are cautious on the energy content or of the food you eat, okay? When you go to Subway, they are mandated to indicate the caloric content of their food. Why? We will talk about in section 5.9 and see how to determine the caloric content of food. Now, 5.1, nature of chemical energy. When we say chemical energy, there are different types of energies, all right? We talked about energy before, And there are two types of energies. We talked about kinetic energy and potential energy. And we looked at how to determine the kinetic energy using the equation that is KE equals to a half times mass in kilogram times velocity square, that is meters per second square. That's what we talked about in the previous chapter. Now, energy, we define that before, and as I said, you should be able to define, those are the key terms, those are the vocabulary. What is energy? Ability to do work or capacity to do work? It is the same thing. You will see this in details in chapter 19, thermodynamics. In electrochemistry, you will cover in details the thermodynamic, which is the study of energy and its transformation, all right? In this chapter, we will specifically look at the thermochemistry, that is the study of chemical reaction that releases energy or absorbs energy. When we talk about the heat evolved or heat involved, think about exothermic and endothermic, because that's where we are going. And how do you know that heat is released? It's by measuring the temperature. All right, so we kind of keep that in that. I don't want to spend time here. I'm not going to ask you to calculate the electrostatic potential when we talk about the potential energy. It is just proportional to the charge, the force of attraction between two charged species, and inversely proportional to the distance between them. I won't go in details into the calculation of electrostatic potential. What I want to just dive into is the first law of thermodynamics. Just forget about 5.1. What is first law of thermodynamics? Remember, when you get to Chem 2, if you forget all what we have done or what we have covered and what we will cover by the end of the, remember first law of thermodynamics states that matter cannot, or I mean energy cannot be created or what? Or destroyed. That's the first law of thermodynamics. You should be able to define that. In this course, I may ask you, which one of the following is the definition of first law of thermodynamics? You should be able to define that. You will go in details. Two laws in Chem 2, it's just for Chem 2. For us, energy cannot be created or destroyed, but it can be converted from one form to the other one. So neither be created. Maybe you are used to saying that energy cannot be created or destroyed. It's the same thing. So to heat your home, energy, chemical energy needs to be converted to heat. Yes, there are a lot of, ways of energy conversion from point A to point B. For example, let me give you a scenario. Here we are talking about the heat, but the energy in the gasoline. Without gasoline, your car will not, will not move, right? So the energy content of gasoline will be converted into mechanical to move your vehicle, converted into sound energy to hear if you're listening to music. It can be converted to heat energy if it's cold and you're turning on the heat on your car. That is energy being converted to other form. Ours is only looking at the heat component of energy conversion. Green plant convert, sunlight to energy. There are so many examples which we will not look in details. All right. So remember, the first law of thermodynamics states that matter energy cannot be created or destroyed, but can be converted from one form to the other form. Okay. Now, when we study, all right, when we study the chemical reaction which keeps away heat or absorb heat, there are terms which I want you to, to really commit to your memory and understand. And I have underlined the word system and the surrounding. If this is my system, right? if this is my system and the reaction is taking place right here, and here I have the thermometer, if the, right, if the reaction is giving away heat, I cannot measure the temperature of the lab. That did the temperature of the lab changes to know that the reaction is exothermic, or did the temperature of the lab decrease for me to say that it is endothermic? No, it is by measuring the reaction by. I know you have done this by dipping the thermometer in your reaction or in your reagents. Upon mixing, you put it in there. What am I saying here? Where the reaction is taking place is called the system. The surrounding is, all right, the surrounding where like the lab is called the surrounding, and then there is the universe. I will simplify this so that you understand what that means before we look in details. This is the system where the reaction is taking place, where your reaction is taking place. It could be A plus B going to C plus D. This is what we call the system. This is how you assign the notation that the system is where we are focusing on. The surrounding now is what surrounds the system. We call this surrounding. This is called surrounding. And then the surrounding plus the universe, everything plus here, we call this we call universe, like that, universe. You saw when we say universe, with the planet where we live, it includes the stars, everything, the sun, you know, the anything out there in the space, even the moons, when we say the universe. So there is the system, there is the surrounding. This will be important in when we talk about the exothermic and endothermic. The point of the universe that we single out or study is called the system. So when you see here the universe, it's confusing if you're looking for the first time and say, that, you know, I didn't know that, you know, my camera is off. I'm sorry about that, but it's not going to change anything. I was saying that the system is where we are focusing. And the universe here is everything. Look at my whiteboard. That is surrounding plus the system give you the universe. So universe equals to surrounding. Sometimes they use that abbreviation plus the sys for the system. And where we are focusing is the surrounding. So understand those terms so that you know what the system is where it's taking place. The reaction where it's taking place here for hydrogen and oxygen in H2O, the system is where the reaction is taking place. Surrounding is, and then everything in there, we call it the universe. Any question on those terms? Any question? So you should know what the system is. That's where we're focusing. And I know this is what's gonna come later on. For exothermic, that means heat is given off exo, and then endo. I'll come back to this. Exothermic reaction, you know what exothermic and endothermic reaction. Just observing heat from the surrounding, giving heat to the surrounding. Now, you know what the system is now. There are three types of systems. There is open system. Open system exchange two things. You have to understand using those terms, if mass and heat are lost, you have to understand to differentiate those three systems. you have to look at it in terms of three things: matter or mass versus what? Versus the heat. Is it being lost or is it being absorbed? For an open system, that means mass and heat are lost. But if only heat is lost but not mass, there's a way we talk about that. So open system, you lose both. So I can say here, open, both are lost from our reaction. If only region of space or the universe being started cannot only exchange heat with its surrounding, no mass, and then we talk about the closed system. So here is closed is heat but not mass. So if the heat is lost but no mass is lost, and then we know that the system is closed. For example, here, note that this is a closed system. Why? If heat is given off, but this mass, remember we balanced the equation in the reaction between hydrogen and oxygen gas, matter cannot be created or destroyed during a chemical reaction, so matter cannot be lost. But if heat is lost or absorbed, there is exchange of heat, and we say that this is closed. You will be given specific reaction and you have to tailor that. Will this be closed system or open system? If both, and then it's open. It's open. That means heat is lost and mass is lost at the same time. Closed system, that means heat is given up. And then isolated system is no exchange, no closed right here. None is lost from the system. That means you will not, heat will be conserved and mass will be conserved. Reaction will take place, but no net change in heat or mass during a chemical reaction in isolated system. For closed system, only heat is lost. For open system, both. I don't know how you want to, prepare your mind, configure your mind, but you should be able to see the difference between the three some. Now, is a human being isolated, closed, or open? Let me see on the chart feature, how will you classify human being? Think about it. Look at my whiteboard and critically think. Is nope. Nope. Somebody say, let's see, isolated. We left it isolated. How do you know that it's isolated? It's closed, it's open. Yes, you're right, David. Is it open? Human being, it is. If you look at the closed system, right here, if we say both, let's say human being and think about like using yourself. Of course, it depends. It can be like, you can argue out, but they didn't give us, condition, because sometimes people lose weight, but there must be some condition, right? You don't lose weight just like that unless maybe somebody is sick, unless you work out, like you really work out for it, and then you're gonna lose weight. But suppose you just, I don't think you will lose, or human being will lose weight just like that to say mass is reducing. So I don't think mass will change. So the only thing is heat will be lost, but not mass. It will be close. So you're right, Jennifer. Close because say if you if you touch somebody like this, you'll feel it is warm, like but they will not lose mass right away. That means they are giving away heat, but not mass. But as I said, we were not really given conditions. Somebody can say, but I've seen human being losing some weight, but unless there's some condition. Generally, right now, you can give away, you can generate, you're giving away heat, and that is why you have what? That's why you have a temperature of 37, all right? There's heat being given off. If I take the thermometer right now and measure your temperature, if it is at room temperature, it is 25, this thing will rise to because you are giving away heat, but you are not losing weight when I'm measuring your what? When I'm measuring your temperature. That means heat is being given off, but you are not losing mass at the same time. That's what I say, that we are not given the condition. You can say, but I know some people lose weight, like they reduce mass. But think at that instant time, if I come to your desk right now, measure your temperature, the thermometer will go all the way, to 37. That's, the normal body temperature, 37 degrees Celsius, or, whatever they say. The temperature, that means you're giving away heat, but not what? But not mass. Somebody say that it is close or isolated. That means if it was isolated, that means we couldn't record the thermometer will not read anything, that it will just remain the same thing. Isolated means neither. That's not true because, human being give away heat. That is why, they measure the temperature, they do the scanning and stuff like that. Does that make sense? Jennifer, you're right, that is it. David, open, if you say open, that means constantly human being is giving away heat. This will help you in other scenarios you'll be presented in an exam or the quiz, all right? So I'll think about through those lines and I'll mention to you why. I know it can be confusing, but you got to think critically. The point is to understand what, what it is. And the way it is right now, it was about thinking that what will it happen? So that is what I wanted to see that. So remember closed system, open system, and isolated and what they mean. So if you look at this, make your own notes so that when you are asked, you can relate to that. You can relate to that. Some problem could be straightforward that a system which loses both heat and mass is called what? A system which loses only heat and not mass is called what? A system which loses mass and heat is called what? And then it's very easy now. But the previous one was a little bit involving critical thinking. Now, let's look at what is internal energy. With respect to the system now, when we say internal energy of the system, you see this term coming over and over with expectation that you know the system, you know the surrounding, and you know the universe. So internal system of the system, internal energy of the system is the sum of kinetic energy and potential energy, which I know we talked about before, kinetic energy and potential energy. We represent this using E. You will see E down the line. We call that the internal energy of the system. Internal energy of the system. So we use E. And E, we can only measure the E. This means delta. This means change. All right. And we read this as change in internal energy, change in internal energy. So when you read that, it means change in internal energy. E is not the same as this. Chemists, they are very specific. You may think that delta E is internal energy. No, E is internal energy, and delta E is change in internal energy. You see this symbol quite often, and it means change. It means change. So by definition, change in internal energy is final minus initial. So change in E is given by E final minus E initial, where it was starting, E minus initial. And this symbol right here, depending on the numerical value you end up with, we use exothermic, endothermic. If less than 0, that means heat is given to the surrounding. From the system is released from the system to the surrounding during the reaction. So this means delta E negative, maybe negative value, means exo. Remember exo? Remember exothermic reaction? I'm gonna come back to that. Remember exothermic reaction? A negative value means exothermic. That means giving heat to the surrounding. Look at this, let me blow it up so that you can really see. If you look at this notation, anything less than 0 is negative. Anything less than 0 is negative. And energy release from the system to the surrounding, we call that exothermic reaction. I know you know what exothermic reaction is. I know you know what exothermic reaction is, so that shouldn't be hard for you to figure it out. All right. So exothermic reaction, endothermic reaction should be easy for you. Exothermic reaction, endothermic reaction. If heat is absorbed, it is endothermic reaction. So positive E means heat is getting in. If delta E is greater than 0, anything greater than 0 is positive for endothermic reaction. For endothermic reaction, so we call that exothermic reaction. So we have the number here for those positive and negative values, the number, the unit, and a sign. We need to have these quantities in order for you to really understand. With respect to internal energy, what does the numerical value tells you? The unit. And the sign, remember the sign, is it positive or is it negative? Let's see each one of them for thermodynamic term. Thermodynamic term, in this case so far, what we have looked at is internal energy. That is what is meant by thermodynamic terms or quantities. So far, we are looking at internal energy. It is a thermodynamic term. What does positive means? Positive means, all right, the system gains energy from the surrounding, and that is endothermic, entering endothermic reaction. Negative, delta E for the result in the system losing, that means exothermic reaction. Negative, negative means remove. Somebody might think that a minus means taking away. No. That's not how you look at it. You have to look at it this way. It's not like something you read over it one time. If it's confusing to you, please understand. Negative means it is given away by the system. And when we say system, you should know the system, the surrounding, and the universe. The system is where we are focusing. That is our what? That is our point or interest. That is where we wanted to have the focus at, all right? That is where we were focusing it. So the interest we have here, let's see, I want to show you I want to share my slide and no, my whiteboard. And this seems to be giving me problem. Let me just cancel this. And I don't want to save that. So system surrounding the universe, you gotta know what those means. The sign of internal energy, all right? We looked at the internal energy and positive, negative, what does negative means, all right? Exothermic, endothermic, exothermic, endothermic, exothermic. I want to share my screen, show you the whiteboard. Exothermic, endothermic. So positive means endothermic, negative means exothermic, entering the system, leaving the system. You have to know the notation. Now, if this is our system, what is in there? All right, it came, it lost. Look at the notation here. Heat in thermodynamic or thermochemistry, we use this symbol Q. It means heat or heat of reaction. We use Q. I don't know why they don't use heat, even though H sometimes is used, but universally Q is used to note down the heat release or heat gain. And then there is the work, which is basically the W work, means when energy, all right, when energy is converted into other form, the energy can be converted into work. For example, you know, mechanical movement of your car, the work is being done. And with respect to change in internal energy, which we defined earlier on, change in internal energy is obtained by Q. Change in internal energy is obtained by Q plus work. Remember, the units for both is in joules, SI unit, all right, SI unit, unless it is in kilojoules or, all right, or calories, you have to change that. So we can calculate the change in internal energy. We know the Q as the amount of heat gain or loss. The sign convention here, with respect to this, I don't know if you want to use the diagram here, that remember the system here. This is where we have the system. Look at my whiteboard. Look at my whiteboard. System. If heat is being gained, that means it is positive Q. If it is being lost, that means it is being taken away. That's how I know the sign convention for heat gain, heat loss. You see here, heat gain is positive. Minus means it is lost. You know, if you look at table 5.1, you may think that this is a bullet point. It's not a bullet point, Look at my whiteboard. It makes sense that the sign convention, the system is losing. You know, on 5.1, you will not know how, how do you relate. But if I have a cartoon on similar to what I have on my whiteboard, I can easily carry in here and say that if it is carrying in there, that means it is positive. And then that means what is lost. Energy being lost, or energy being gained, positive, negative. Now the terms used for negative and positive W has to do with the work done by the system, work done on the system. Work done, all right, work done on the system. Look at the W, that means the surrounding is doing work on the system. Positive, work is done on the system. The system is doing work on the surrounding, it's gonna be negative. It's gonna be negative. A time will come where you have to assign the numerical value, sign convention, so that when you look at this equation, the numerical value for change in internal energy will be the function of what is the sign convention for Q, what is the sign for W. Those little minor things will really throw you off, because you will think that it is a one-size-fits-all equation of Q plus W, and then boom, I end up with the answer. No, it will boil down to how the sign convention. For example, if I say work is done by the system, that means my symbol here will be plus negative W. If heat is being lost by the system, it will be negative Q. If heat is being gained, that means positive. If work is done on the system, this will be positive. So here, W and Q has to do with the sign convention, all right? Once you have this general equation, you will have to understand, is it work is being done on the system, or the system is doing work on the surrounding? And then you pick the right convention. And then you see now the net change, okay? It will just be clear what the symbol will be, what the symbol will be. In this chapter, what makes it, I know maths is a challenge to some of us by itself, but when we come to sign convention with respect to this equation, it will be so complex, because you think that all I have to do always is to add. No. Pay attention to when they say work is done on the system, what will be the sign convention? What will be the sign? Okay. You'll be asked question on that. Now, how do you know that heat is released, or how do you know heat is gained? It's by just measuring the temperature, all right? Heat is absorbed if the reaction is, all right? It is absorbed if it is endothermic. How do you know that it is endothermic? It is absorbed from the surrounding. Key thing is knowing what is the system. Let me give you something you can do at home today. If you have an ice cube, if I have an ice cube and hold it like that, what will happen? It's gonna be cold. What will happen? The ice cube will melt, right? The ice cube in that case is the system. It will absorb heat from the surrounding. The surrounding is your hand. The heat from your hand will get into the ice cube, and the ice cube will melt. Some solution apply the same thing. So relate the exothermic, I talk about the exothermic and endothermic, you know what that means. Heat is released, it is absorbed, all right? Q, this is exothermic. We don't use exothermic for W, and this is endothermic, endothermic reaction. Endo and exo. So you should be able to know what that means, all right? Any question on exothermic, endothermic, exothermic? I don't know those terms. Now let's shift gears to what we call state functions. In thermodynamics, there's those, all right, there are those terms which do not depend on the path taken is only depends on the final and the initial starting point. We call those state function, and one of the state function in thermodynamic is the internal energy. It does not depend on how you get in there. Elevation is an example of a state function. All right, does not depend on the path taken in there. Internal energy is one of the state function which do not depend on how the system achieves the final state. It depends only on the final and the initial state. Internal energy is a state function, which means the final and initial only determine, but not the part taken. A real example is, or just give you an example, if this is a mountain, right? If we want to get at the top right here, some people can go, can start from here. I use elevation as an illustration. Some people can go this way and they get right there. They'll have an elevation like that. Some people can go this way. Does not really matter how you end up. At the end of the day, the elevation from the sea level to high level right there determines how high you are at the time you are at the top. It does not depend on the path taken. It can be straight, it can be zigzag, but the elevation is a state function. State function also is, internal energy in a similar way is a state function. It doesn't depend on the final, on the path taken, but it only depends on initial and final, but not the path taken to get in there. All right. However, the Q and which is the heat and W, which is used to determine the change in the internal energy, are not state function. They are not state function. Okay, they are calculated differently. So no, the internal energy is state function. Now, some systems do expand, some systems do contract sometimes. We call the work done by the system BV work. BV, pressure volume work, all right? Pressure volume work. And for a closed cast, the system can either do work, it can either, or work can either be done on the system. The illustration here shows the work, BV work, and work in pressure volume work is given by this equation, BV times change in volume. This is the equation for calculating work done by the system. This is the equation. There is a negative. This change, delta V means change in what? This means change in volume, change in volume. And the volume has to be in liters, all right? Volume, all right, this volume, and I'm going to show you why volume is always in liters. Pressure, all right, pressure, all right, always in atmospheres, ATM. I don't know if you know, in most cases you'll be given pressure anyway in atmosphere. I don't think somebody will just mess you up giving you in torrs or in millimeter mercury. No, we're gonna talk about that in chapter 10. So remember, pressure has to be atmospheres. This is ATM. And our volume has to be in liters to apply this equation. W equals to PV, change in volume. change in volume is given by, you have to do this, change in volume is V final minus V1, V initial, V initial. Change in volume times V initial, all right? So that changes the value. If I have this equation, all right, work equals to negative PV change in volume. If this value is negative, negative and negative changes to volume. So it has to do with change in volume, just subtract final minus initial. If you end up with a negative, you multiply by this negative, it's positive. So that's what you need to remember. If you multiply, all right, if you multiply the units of pressure, all right, multiply the units of pressure, you will end up with this. The units will be liters times atmosphere. Remember, the volume will be in liters, the volume will be in liters, and the what? And the pressure will be in atmosphere. It turns out that 1 joule, remember this, and I'll give you this in the formula sheet, 1 joule equals to 1 or 1.3 liters times atmosphere. This is what you will need as a conversion to change the value to units. For example, if I look at this one will be my last example. If I look at on my slide, calculate the work in joules of a system which contract from to. So V initial or V final equals to 0.85 liters. V initial equals to 1.55 liters. So we don't need to change the volume to liters. So V change in volume is given by V final minus what? V initial, V final. So if I subtract that, 0.85, all right, 0.85 minus 1.55, I end up with negative what? Negative 0.7. This is negative 0.7 liters, negative 0.7 liters. So multiply by the pressure. So if I multiply by negative, remember work, all right? This one right here, work is given by, this is the equation, change in V, which means negative 0.985 ATM times negative 0.7 what? 0 liters. So if I multiply by that, 0.7 times 0.985, I end up with positive what? 0. What? 0.6895. This is liters times atmosphere times now 101.3 joules over 1 liter times atmosphere. So that will cancel out, times what? Times 101.3, and it is 69.8. This is positive 69.84 joules. That means work is done on the system. Work is done on the system. I want you to read on this. What I'll do is I will make quiz on chapter 4 available, quiz 4. Please, I'll send you the study guide for the quiz and make you, all right. What is the conversion factor? Yes, I had given you that. The conversion factor is right here. I'll give you this. This is the conversion factor. I'll give you 1 joule. No, 1 liter atmosphere. I should be right here. Sorry about that. 1 liter. The conversion is right here. 1 liter times ATM. So equals to 101.3 joules. This is the conversion factor. This is the conversion factor we will have. So the conversion factor here is, so for that, it should be, this should be to convert that 1 liter atmosphere. You see, I have joules at the top. That is our conversion factor, 1 liter atmosphere. So here, Anthony, this is the conversion factor. 1 liter atmosphere equals to 103. All right, 103. I'll give you that in the test. But when you do the homework, have this ready, because you may get stuck and say, how am I going to change this to that? All right. The class is dismissed. We will meet next week. Sorry for taking a minute. I'll see you on Tuesday. As I said, I'll send more information on Peace Chapter 4. Have a good day, everybody. Thank you for tuning in. I'll see you same time on Thursday. Peace safe.